moment here and kind of run through that. I'll just kind of talk about that section a little bit and do a couple of examples. Won't do anything super in-depth because you guys have already read this and worked on the homework, but no harm in just kind of clarifying some of these concepts, right? So the polar coordinate system, the points that you're plotting are r comma thetas. So it's basically a radius or a length and then an angle measure. So ostensibly what we're talking about is equivalent to kind of plotting a vector, right? Where you have a magnitude and a direction, kind of. So if we wanted to plot, say, 3 and 120 degrees. So these circles each correspond to a radius. So the first circle is like radius 1. The second circle is if radius is 2. The third circle is radius of 3. So I'm going to be plotting somewhere here on this third circle in this problem. Everybody okay with that idea? And then to plot the angle of 120 degrees, we're going to think about this the same way we did before in first semester. So we have our initial side of our angle. And each one of these little lines is basically a 30-degree angle. So it's 30, 60, 90, 120. So here's r equals 3 and 120 degrees. So the point 3 comma 120 is just kind of the intersection of that circle with that angle. Everybody okay with that idea? So not too difficult there. What probably deserves a little bit of clarification would be, what do we do with something like this, where we have a negative angle? Or I'm sorry, a negative length, right? A negative radius. Now that doesn't make a whole heck of a lot of sense, but if we think back up to thinking about this as a vector, that kind of helps. So again, if we think about this as a magnitude and a direction from a vector, if I have a positive vector and a negative vector, if I take the negative vector, basically I'm just reflecting it across, going the opposite, pointing the opposite way, but still having like the opposite direction as before. Everybody okay with that idea? So we're going to think about this the same way. So I'm going to start with just a radius of 2. Which is here. And then the angle I'm going to have is, remember, pi over 3 is equivalent to 60 degrees. How do I convert between radians and degrees again? Yeah, so I multiply this by 180 over pi will get me to degrees. So 60 degrees, our initial side is here. And then our terminal side would be here. But since we're talking about a negative radius, what I'm going to really look at is this angle, which is like the opposite vector there. So this is my point down here. Everybody's okay with that idea? Again, not terribly complicated, but, worth going over. So note that this point would also be equivalent to positive 2, and then pi from here to here is pi degrees more, 180 degrees more. Everybody okay with that since it's just a straight line? So that would be like 4 pi over 3 would also be that same point, right? So we're going to definitely get some coinciding points here on dealing with polar coordinates, where you can have the same point or different points occupying the same location. Everybody's okay with that, as we've just demonstrated here? Now, how many different points are going to be able to occupy each location? Well, it's at least 2, right? We've shown that that's going to be possible. Is it going to be more than 2? What if I wanted to also plot the point 2, 10 pi over 3? Well, let's maybe write it a little bit more intuitively. Let's write it that way. What can we say about that? Ben? Yes, very good. Exactly right. So again, this is just a full rotation. So 4 pi plus a full rotation, or 4 pi over 3 plus a full rotation, is still going to end up at the same spot. So this is also occupying that same location. Everybody agree with that? And how many coterminal angles can we find for a given angle? Ben? Yeah, exactly right. We can do an infinite number of coterminal angles for any given angle, because you can just do another rotation forward or backwards, right? You can keep going forward or you can keep going backwards. It doesn't really matter. So yes, there are infinitely many points that are coinciding in the polar coordinate system. So to just kind of formalize that, or if you prefer to be working in degrees, where k is just an integer. So that's a way to find a coinciding point, or to check if 2 points are coinciding. You can kind of use that generalization there. So let's say we wanted to find all the points that coincide with this point. Well, one set of them are going to be very easy. Where the radius is positive. We just find everything coterminal to the given angle. And if the other set is going to be where the radius is negative, where we add 180 first, and then we find everything coterminal to it. And we could clean that up a bit and just call it like negative 54. Be the standard, but since again we're kind of taking notes, I figured I'd just write it that way. Is everybody okay with this notion of just going and checking if, or finding things that are coterminal, or you could use that rule to kind of check if a given 2 points were coterminal, or not, sorry, coinciding. Okay. So the next idea here that we'll talk about is converting back and forth between rectangular coordinates, so things in the xy plane, with polar coordinates, these r comma thetas. So we're just talking about kind of translating between xy coordinates, i.e. rectangular coordinates, or r comma thetas, aka polar coordinates. So the tools that we're going to use here are the following. So I know that, let's draw a picture here maybe first. So if I have it here, where that length is r, and this angle here is theta, I can translate that into, and I want to know this xy coordinate. I can just kind of turn this into a route, right? This is basically what we did in first semester when we kind of defined sine and cosine. You kind of remember this? So one thing that we can say is that so r squared should equal x squared plus y squared. We know that x is going to equal r times cosine theta. I will equal r sine theta. And I'm going to put a little star next one because that one is, we have to be careful using, right? Especially if we're using that to find theta, which is the time we'd most often use this. Because we might be having to add or subtract from a multiple of 180 doing that. So let's do an example here. Let's take the point, the polar coordinate, -3, 148 degrees, a rectangular coordinate. Well, I know that x is equal to r cosine theta. So in this case, that's -3 times cosine of 148. And when I type that into my calculator, and the y I know is r sine theta, and type that into my calculator, I get about -1.59 there. And if you plotted these two and like superimpose them, you should see that those are coinciding, right? Let's go the opposite direction and let's take a rectangular coordinate and translate that to a polar coordinate. By finding the r, because I know I can just use the Pythagorean theorem to do. So what? That's the square root of 13 or something. Oh. Well, that's why that's supposed to be. I squared it before I wrote it down, and then I still put the squared on it. Mr. Kulik, come on, get on it. I can do better, I promise. Okay, so there's my R. To find my theta, I have to be a little bit careful here. So if I plot my point negative, and that's the theta that I actually want. But what I'm going to be finding is this value, say, call it alpha, because I know alpha is the value of y over x. So then I can say theta is 180 minus alpha. Right, you guys kind of remember doing this? Again, this is a first semester concept when we were finding values using these inverse functions. So in this case, we have -3, and that comes out to be about 33.69. So that one's about 1. So there's my polar coordinate. Is that okay with you guys? Again, I bulldozed through some of that, but you should have already kind of read through this section and done some homework on this idea. So it's not like you're coming in cold to this. So I went a little bit quick, maybe through it and hand waved some ideas. But again, it's not because we're baseline there to draw from. Now that we've talked about that section 10.3, and that's about all the content from 10.3. I'm going to pause with the content and ask if we have any questions. We've now talked about, at least in class, all the concepts that were kind of covered in the most recent homework set. So if there's anything that you guys want to ask about now, that would be a good time. And then we'll go on and do another section. But I figured I'd wanted to talk at least about polar coordinates first to kind of cut off any of those sort of questions at the past, or at least build us a foundation if we're going to ask about those. Teresa. Certainly. I kept wanting to call you Melinda, but it's the wrong Fadul. Okay. So we are given a parametric function as follows. And what are we being asked to do this? Eliminate the parameters and find the domain and range of the resultant function. Okay? So to eliminate the parameters, this is one of those special case situations where this is a circle. So the way we'll eliminate the parameters is a little bit different. Before I jump into this, let me just go back and double check exactly. And in case you weren't certain on sight of looking at this and knowing that it was going to be a circle, starting just by looking at the parametric graph would have been potentially helpful here to justify to yourself, like, oh, hey, that's a circle I'm looking at. If my calculator wants to load up here, we'll take a quick peep at the graph here just to prove to everybody that what it is we're looking at is indeed a circle. Oh my goodness, come on, computer. Anytime. Do you wanna, are we opening? We stalled, what's going on here? Oh, finally. It's probably going to open about 35 times here, huh? All right. So I'm going to go ahead and turn this into parametric mode. And we'll do 4 cosine t, and then -4 sine t. Ugh. -4 sine t. And I'm going to get rid of this other mumbo jumbo here. And we're going to, our range for t, it tells us, is 0 to 2 pi. And I didn't even go back to look to make sure I was in degree mode, or radian mode, excuse me, but I am, okay. So let's hit graph, and what we get is here a circle. Okay. So now for a circle, if you recall back, or really for us, it's enough to just think about it as a Pythagorean theorem situation, because if I look at my graph, where's that circle centered at? The origin, right, 0, 0. And here, my h and k is the center of the circle, is what the h and k represent. So pretty easy to see that that equation is just going to turn into x squared plus y squared. So now I can just kind of, oops. So far, so good. Okay. So that's going to give me 16 cosine squared theta. I can factor out the 16. And then I recognize cosine squared plus sine squared is equal to 1. So that tells me that r squared is 16. And since I know that h is 0 and k is 0, what I really have is equal to y squared. Or if you really wanted to, you could write it this way. If you really wanted to really hammer home that the center was at 0, 0, you could put the zeros there, but whatevs, you don't need them. Does that feel okay there, Teresa? Yeah. And I think they'll all go pretty similarly looking at it. I don't think you'll have, I think they all have center 0, 0, so it's like reveal from there after you've done that once. At least when I say 26, 27, 28 are all kind of similar. Is that what you needed? Great. Just 43. Let's see. It says Jake hits a baseball when it's 4 feet above the ground. Initial velocity of 120 feet per second. The ball leaves the bat at a 30-degree angle. With the horizontal and 30 degree with the horizontal, and heads towards a 30-foot fence. Let's say there. That's 350 feet away. Write the parametric equations to model the flight of the baseball. Okay, so if we're talking about the path of a ball, we're talking about the position. So I want the position function. So if I go back and look at the notes here, that equation is the initial velocity times cosine t or cosine theta t, excuse me. And the y coordinate is -16t squared plus the magnitude of v, the initial velocity, sine theta t, plus initial height. So for us, that initial velocity was 120. Our angle was theta. Our initial height was 4 because the ball was 4 feet off the ground. So that's part A. Just filling in the formula. Part B says if no fence or other obstacles are present, find out how far the ball would travel when it first hits the ground. So the idea here is I need to find out how long the ball was in the air. So basically, I'm going to solve y of t equal to 0 for t. And I'm going to use that value of t to plug into the horizontal vector to find out how far the ball goes. What's up, Ben? 30. You're welcome. Is everybody okay with that plan? Jess, you good? Yeah. Okay. So I'm going to take my y of t coordinate and set it equal to 0 and solve that for t. Quadratic function, because the sign in there, it's not likely that this is integrable. Even if it was, I'd probably just still opt to use the quadratic formula anyway, since the leading coefficient isn't 1. It's going to be kind of a pain in the butt to factor it, even if it is factorable. So I'm just going to go straight to doing the quadratic formula. So t equals -109.30 squared minus 4 times -16 times 4. All over 2 times -6. So I'm going to type that into my calculator. I'm going to do it all in one line because I'm fancy like that. To make sure I don't screw up the parentheses, I'm going to use the fraction option by pressing alpha and y equals and choosing the first option, numerator over denominator. It just helps me kind of keep everything in line because I'm able to just kind of write it the same way it looks. Now I can't do a plus or minus on my calculator, so I'm just going to write as a plus first. And depending on what my answer looks like, I might have to go back and look for the minus also. Everybody still good with what I'm doing here? So I do that, and I get negative 7.4. Well, that hardly seems correct for us, so let's see what the answer is. Oops. If I change that from a plus to a minus. What did I goof up here? I did goofed something. What did I goof? Ah! Expert. Thank you. All right. So I got that there. Okay. So with the minus, it's 3.8. And the other one, it's going to be something outrageously negative and small. I know for a fact, because I've done this problem already. Yeah. So I want the 3.8, right? What is that negative 0.06 really representing? It's talking about that spot right there, as if like the ball continued to travel like in the opposite direction or something. And that's what that other end of it is really kind of representing. Not very interesting. So then I'm going to do x of that 3.82, which is 120 cosine 30 and then so I'm going to do 120 times cosine 30 times that previous result. And that gives me 396. Jess, are we good there? Yeah. Okay. So the next part, part C, says, will the ball clear the fence? If so, by how many feet? If not, will the ball be catchable? That is, will it be less than 10 feet off the ground when it gets to the fence? We're assuming that we don't have any, like monstrous baseball players that are like 30 feet tall that can catch a base, we got to be able to jump and catch it. Probably can't have a man jump more than 10 feet up in the air with their hand up. It's like the height of a rim on the basketball. So you're still a heck of a jump. So what we need to do is we need to find out this is our thoughts. So what I'm going to do is I'm going to solve x of t equal to 350 for t. And then I'm going to plug that into y of t and compare that to is that, and look at that height, right? If it's greater than 30, we clear the fence. If it's less than 10, it's catchable. And if it's somewhere in between those, it's probably like a double off the wall or something, right? For those baseball players out there. Cool with the plan? Okay. The nice part is solving x of t is much easier than solving y of t, because x of t is just linear. So I have 120 cosine 30 t is equal to 350. So got to be careful with our parentheses here. So I'm going to just type it in this way. So 350 divided by 120 times cosine 30. I'm going to write it as a fraction like I would on my sheet of paper. And that gives me about 3.36. So y of 3.37 is equal to negative 16 times my answer squared plus 120 times sine 30 times that answer plus 4. So that gives me 20, since that's less than 30, it's not a home run. And because that's greater than or equal to 10, so this is like a double or something. It's going to bounce off the wall, but high enough up that the dude couldn't catch it. Unless he did some crazy ninja stuff and like ran up the wall and jumped or something. But we're assuming Spider-Man doesn't play center field for this baseball team. Jess, does that feel okay?
Yeah.
Okay. So again, the trick is just kind of like going back and forth, like solving one of the parameters and plugging it into, the result into the other parameter to kind of get what you need. Yes, sir.
I got kind of lost when you went from, like, when you set y of t to 0, and you went from, like, the equation to, like, actually solving it. I don't know, where I got lost, but you, like, just do that again, I guess.
So you're talking about at this spot?
Yeah.
So that's just the y of t function set equal to 0, right? All I've done is I've taken that and filled into the quadratic formula. So, like, x equals negative b plus or minus square root b squared minus 4ac all over 2 times a. So like my a is the negative 16, my b is 120 times sine 30, and my c is 4. So I plugged that into my calculator. I got 2 results. I got that 382, and the other one was like negative 0.03 or something. And I discarded that one. Now that I know how long it's going to take to get to the ground, I can plug that into the horizontal component, and I can use that to figure out how far the ball goes.
All right.
Which is what I did here, is I just plugged that into the x of t to find out how far the ball went. So the y tells you how long it's in the air for, and then you can use that to figure out that answer, plugging it into t, or plugging it into x of t to figure out how far it goes, left and right. Or the result, the opposite, is what we did in C, where if we know how far we're going, we can plug that into x of t, solve for t to figure out how long it takes to get there, use that result in y of t to figure out how high it is up in the air at that point.
All right.
Does that help kind of see what we're doing?
Yeah.
So it's just about like, okay, do I know how far it's going or how high it's going to be? Will dictate which one you want to solve, whether it's x of t or y of t.
All right. Thank you.
Yeah, no problem. Last call on these. Okay. We can always come back and ask more later if you decide later on that you're like, yo, I take it back. I do want to talk about something more from there. Totally fine to come back to it. So today we want to talk about polar functions. So last time we had talked about here and there, so I just wanted to kind of write them down again right at the start so that we don't have to go back and like re-justify them, but those are things we'll need. So let's just look at an example of a polar function. Let's say we have r is equal to 6. Go ahead and open our graphing calculator and graph this, just to kind of show you what graphing looks like when we're in the polar mode. So I'll take my calculator, I'll go to the mode section. I'm going to change it back to radian since we're graphing, and I'm going to change it from parametric to polar. I'm going to go to the y equals, and here I'm going to type in 6 cosecant theta. Now I don't have a cosecant button on my calculator, but I do remember that cosecant is the reciprocal of sine. So I'm just going to instead, everybody cool beans there? I'm going to just go to my window button. So my interval over theta, since we're graphing a trig function, 0 to 2 pi seems perfectly appropriate there. And then my xy scale is just going to be my standard -10 to +10 for both x's and y's. So that all looks good. So let's just hit graph and take a look at our result, which is a horizontal line. That's pretty boring. Why the heck is that just giving me a horizontal line? Well, let's investigate, right? So this just looks like the horizontal line like y equals 6 to me. Why the heck is this giving me just a horizontal line? Well, so as I noted earlier, sine, so I can just rewrite that as 6 over sine theta. If I then multiply by theta, I get that r times sine theta is equal to 6. And if I look at my list here, I know that y is equal to r times sine theta. You're welcome. Abby, you have a get out of jail free card. Abby M. I guess we have 2 Abbies right in a row. You're welcome. And we have just that y is equal to 6, which is the graph of a horizontal line, which seems to jive pretty nicely with what we just got. Everybody okay with that? Ben?
You got r sine theta is equal to y because like up there.
Yep. Yep. Just using that identity from before. Let's do something that's a little less trivial. Let's do r is equal to 6 cosine theta. Before we translate that into a rectangular equation, let's just take a look at what the graph of this is going to look like. Okay, so it looks like I have a circle. Everybody agree with that? The center of that circle appears to be at what? Looks like 3, 0. And the radius of that circle appears to be 3. You guys all kind of buy that just looking at the picture? Okay. let's see if in converting this into rectangular coordinates, we end up with the equation for a circle with that center and that radius. Okay with that plan? Oh, good. So since I know that I'm going to be hunting for a circle here, since I've looked at the graph, I'm going to start by multiplying both sides of my equation by r. Because I want to get an r squared there, because plus y squared. In addition, r times cosine is just x. Is everybody okay so far? I'm just writing on the right-hand side what it is that I did, just for clarity's sake. So now I'm going to subtract the 6x from both sides. And I want to look like x minus h squared. Well, we know how to do this. This is something you would have done last year in your Algebra 3-4 course. This process is called completing the square. Yeah. So let's just do a little aside here and review that process once generally, and then we'll do it specifically for this problem. So I use CTS for completing the square, just an abbreviation. So let's say that we have some quadratic that we want to complete the square with. The first thing I would need to do is to make the leading coefficient equal to 1. So I'm going to start by just factoring out the leading coefficient. And then I need to add and subtract 1/2 of that null term. So just 1 b over a is b over 2a. Right, because to divide, you just make a reciprocal and multiply. Everybody's okay there? Notice that b over 2a squared minus b over 2a squared is just 0. So I haven't really done anything. All I've done is really added 0 there. Right, everybody see that? I'm going to distribute that leading coefficient, or distribute the a to the last piece I'm subtracting, just so that I can kick it out of this set of parentheses I have there. This piece, by definition, is now a perfect square. And I'm going to factor that using that perfect square factoring pattern. So that's me just kind of running through again what that completing the square process looks like, really generally using like just a generic quadratic. Let's do it now specifically for x squared minus 6x, which is a heck of a lot easier to see what's going on than what I did there in general. But I figured we had to kind of review the process at one point because, well, you don't spend a lot of time doing it in Algebra 3-4, but we're going to do it quite a bit this chapter, so, or at least this section, I should say. All right. So x squared minus 6x. The leading coefficient is already 1, so I don't have to worry about that very first step. So I'm just going to start by taking that null term, dividing it by 2, and then adding and subtracting it. Everybody's okay there? That part is a perfect square. Oops, x squared. So a vector, and then -6 divided by 2 is just -3, and -6 divided by 2 squared is 9. Everybody good there? So what I have now is I have x minus 3 squared minus 9 plus y squared is equal to 0. And all I need to do is add 9 to both sides. What I have there? Well, that's the equation for a circle whose center is 3, 0, and whose radius is 3. Exactly what we thought we should be getting. So it's very nice having the graph to look at, right? It basically tells you the answer that you should be arriving at. Your job is mostly just to fill in the algebra kind of in between. Let's do another that's even a little bit more complicated yet. The nice part is that the process isn't really going to change any from what we just did. I'm going to start by multiplying both sides by r, because I want an r squared, because I know r squared is x squared plus y squared. I also know that r cosine theta is x, and r sine theta is y. I then can move things onto the same side. Oops. And I have 2 completing the square problems then to do. Right? I have to complete the square for x squared plus 5x. And I have to complete the square for y squared minus 4y. Everybody okay with that notion? So since the leading coefficient is already 1, I'm just going to add and subtract 5 over 2 squared from the first parenthesis. And in the second parenthesis, I'm going to add or subtract -4 over 2 squared. I'm going to kick out that last term and then factor the remaining stuff as a perfect square. And then my last thing to do is combine the like terms between -25 over 4 and -4 and add those to the other side. So when I do that, I need to make a common denominator. So 4 is really 16 over 4. And 16 over 4 plus 25 over 4 is really 21 over 4. So what we're looking at here is a circle whose center appears to be -2.5, comma 2, and whose radius is between 6 and 7. No. like between 2 and 3. No, a little bit bigger than 3. Right, 41 over 4 is a little over 10. 10 is a little bit more than 9. 9 is 3, or 9 squared, or 3 squared is 9. So let's just go take a quick peep at this and see if that's what we're getting, is a similar circle. Right, so I have -5 cosine theta plus 4 sine theta. Let's take a peek here. So it appears the center is -2.5, 2. That looks like right about the right spot. And the radius there looks to be more than 2.5, pretty close to 3. That's about right also, so I'm pretty confident that I've done this correctly. Be okay with that? Now let's try doing some where we go the opposite direction. Let's take a rectangular function and convert it to polar. So we'll start with something real trivial, like y equals 4. Well, I remember that y is the same thing as r sine theta. And to get a polar function, I need the r by itself, so I'm going to divide both sides by sine theta. And I remember that 1 over sine theta is the same thing as theta. And so I'm done. Right, I have a function in terms of r and theta. Not so bad. Let's do something a little bit more challenging. So my first plan is going to be to FOIL everything out. So remember that x minus 3 squared is a foiling exercise. 3 times x minus 3. It's not x squared plus 9. Similarly with the other piece. Everybody so far so good? Okay. I'm going to group together the x squared and the y squared because those become, oops, that's supposed to be a y. Because those are just the same as r squared. X is the same thing as r cosine theta. Y is the same as r sine theta. And if I subtract 45 from both sides, I get zeros. They just cancel out, right? So I'm going to get add the r, or 6r cosine theta to both sides and subtract the 12 sides. And we're almost home, right? Our polar function shouldn't start r squared. It should start with just r. So what do I want to do here? Ben? So you'd think that you'd want to do that, but we're still left with r's on the right side of the equation, which we don't want, right? A polar function should have 1r solo on the left-hand side. So we are going to divide by r, but why in this case are we allowed to divide by a variable when that's been a no-no in algebra all this time up into this point. What is the potential pitfall with you when you divide by a variable? Victoria?
Because you don't know what it is.
Because you don't know what it is. It could be what value? 0, right? Now, what is R representing again? It's a radius, correct? Can a radius be 0? No. So it is okay to divide by R in this case because R is a radius and it is non-zero. So it is okay to do that. I just wanted to make sure that we explained why in this case before we went ahead and did it. Because this is a place, again, where students often love to divide by variables. It's like, oh, no, you can't do that yet. And if we were to graph that, you're going to see that it does match a circle whose center is at 3, -6, and whose radius is between 6 and 7. Is that okay with you guys? That's it for this section. We're going to stop there. I think we still have one more section to look at in this chapter. As far as the homeworks go, on 63 to 70, to convert the polar equations to rectangular and then identify the type of the graph. I don't think that we have enough. I think the type part comes in the next section, but you could do the converting right now. And then you can definitely do 73 to 84, which is converting rectangular to polar. That you have enough to do. And the rest of these questions are all going to be from the last section. So we'll probably finish up the lecture for this chapter this week, and we'll probably be testing next week, would be my suspicion. Okay with that?